Hi, in the study of the previous subtopic, when we are studying the concept of motion in the version of translational, so we observe that it happens because there is what we call force applied. Now, the core concept of what is torque itself is because of what is the cause of changes in the rotational motion. And the answer is yes, torques. Okay. To understand regarding torque, we are going to see an example of opening a door. And opening a door here represents the concept of rotating the door. So here we will find that when a force is exerted on an object where the object is pivoted about an axis, the product will tend to rotate, and that rotation is the effect where we call it as the torque. Now, according to these few figures, 6 figures altogether, opening a door will give you a maximum torque. This one. Observe that the force by pulling the handle on the knobs is applied here, whereas to open the door, or should I say rotate the door, will give you no effect, no torque for the case when you apply the force on the hinge pada dia punya tepi ni dekat axis of rotations. Now, same goes as the second figure, no effect as well. Why? Because the force is applied as such a way. So here we find that no force is applied. However, not necessarily it will produce the rotational motion. In short, the torque product. Hence, we find that not all forces will produce rotation. Therefore, it depends on two things. Number one, where it's applied. Number two, the angle. Number two is the angle. Look here at the figure, a wrench. Observe that you would like to rotate it. By applying a single force as such, you will find that you can open up the force to two components as in the figure. However, rotating would be due to this force alone, F sine theta. F sine theta. F cos theta would just produce this wrench to be taken to the right. So, no effect of the rotation. Now, by considering the two things just now, the angle and the location, you find that torque, which is a symbol of tau, Greek symbol, is the product of R times F and sine theta. So what is theta? The angle between R and F. The angle between R and F. Look at the figure, similar as this one. And what is R? As R is the distance from here, from axis of rotation to where the force is applied. Now the R is also called moment R, lever arms, which is a product of R sine theta. Going back to this figure again, now it makes sense from the calculation. Why is it that there is no effect for both figures? The first case here is because there is R value equivalent to 0. This is the axis of rotation. However, here is because of the theta equivalent to 0. And again, it makes sense that this one will give you the maximum effect. Why? Because R is the largest possible. Now, there are two reasons that being the maximum effect. So, aside of having the largest moment arm, what is the other answer? Think about it. On the other hand, let's compare with something you have seen earlier in the case of the work. Okay. Recall that when you look or you consider the calculation of work, it's the same expression except that the angle is cos theta, and bear in mind that F and the displacement or delta R must be parallel to one another. So yeah, work is a scalar. But what about torque? So torque is a vector. Since it's a vector, then you must consider the directions. Let's look at how direction is being considered by the book. Now, similar to forces that they are vectors, you can add them up. Now, that's the same thing when you do for torque. You can sum them up. Now, how to do the summation or what we call as net torque? Look at this figure. This is an axis of rotation. So, where it doesn't change, if this object, the whole object here, tend to rotate because of torque or because of force applied here, in which direction would it rotates? Here. What about this one? Now, you can use this by using your pencil. Hold your left end of the pen. Okay. Put your pencil horizontally, like this. Okay. And hold it here at 0 on the left end. Now apply the force in this direction, similar to F1 just now. Observe that it rotates as such. Now this rotation, if we read by the angle, it's actually measured as if there is an axis, imagine axis of rotation, and this is the rotation. So the angle is above from positive x-axis. So that's how we consider that this torque due to F number 1, or we might write it as tau 1, is a positive value because of the direction. To make it much simpler, counterclockwise is a positive value. What about F2? Okay. Now, this F2 will make this object rotates clockwise. How? Now, I'm gonna sketch this here. So, it probably looks something like this. Okay. The direction as this one. What do you see? You find that this object now has a tendency to rotate here because you are holding your pencil over here. So, applying force in the directions as F2 will result your pencil rotating downwards. And because of that, you find that this direction is clockwise. Opposite to counterclockwise, it shows that as if the angle covered by F number 2 here is traveling a distance from below positive x-axis, and that is the reason why you consider this as a negative value. In short, measuring the net torque will give you a product where minus torque number 2. Now, you might be confused, why is it that in this equation there is no angle involved? Well, go back to the figure. Observe that there is an angle, however, it is 90 degree. So, both actually has 90 degree. But not shown here because sine 90 is equivalent to 1. So, that's basically how you sum up torque, by looking at how the angle covered due to the rotation. As you can see here in this figure, shown how torque produce rotation to this screw. Okay, so look at how the direction of the torque in the shape of a curve. However, from our angle, we find that it's a little bit confusing, right? To see whether the angle covered is positive or negative. Hence, we have another way or another technique which can simplify this figure. Therefore, there is another technique that you can use by using your hands, okay, to indicate this direction of the torque. How? Look at this figure. Okay. Now, what you need to understand is the direction of the torque is your thumb. Direction of your thumb. So, if your thumb is out of the book, that's the direction when it's positive. So, in the case here, okay, you find that the direction of the force applied would be similar to your curling fingers. Okay, or your direction of force. So therefore, we are going to use this figure, this technique, so that we can produce the direction in easy version. Let us look at example 10.3, where in this example 10.3, we are going to determine the net torque, so summation of torque. We are given two forces like here, where the forces here is labeled as T1, T2. Now, so to do the torque, we are aware that the value of T would be time with the radial arm. So the first torque here, coming from tension 1, we are going to jot down as T1, equivalent to the product of T1 times R1, because this is where the force is applied, and to where the force is applied and the distance towards axis of rotation is R1. And because the angle is applied perpendicularly, product of sine theta. That goes the same thing as T2. But the thing that I like to highlight is, let's use our curling finger. Now, curl your hand so that your thumb is in the direction, your curling finger is in the same directions of the T1. You will observe your thumb is into the page. So this will give you as if this is the rotation. So thumb into the page, or the curling direction. You have two methods here. You can choose by using this one, where this is considered as clockwise, negative, or you can use the version that your thumb is into the figure, indicating that is a negative. Salah satu guna, cukup. And you find this one, curling your finger will allow your thumbs out of the page. Your thumb is out of the page. Because it's out of the page, you find, yes, torque for number 2 is a positive product. Let's double check that this is positive and observe this is negative. Alright, for those who are having trouble, why all of a sudden they use T, just observe it's actually just a symbol to present force. Nevertheless, for B itself, now they give you the value of the force individually, including the value of lever arm. So substitute accordingly, and you will get the value of the net torque itself. Observe that the unit here is purely coming from the expression. Since torque is F and then R Newton meter. Now, the value being a positive value indicates that it will be in the position in the direction of the counterclockwise directions. Now that you have seen the idea that torque can be added because they are vector, so what happened next is that you see the similarity when you deal with Newton's second law, ma. So you find as well, torque is the very reason why object rotates and accelerates. So when you have a value of a net torque, meaning to say the net torque is not zero, so you find as well the object will accelerate, however, in a circular motion. It's interesting to compare that this is acceleration in the linear direction, where you will find related to what we call as tangent, and here is acceleration occurring in the rotation. Now mass is a quantity where you relate with what you call as inertia, and notice that the I here is a symbol which is called as moment of inertia. Now, this moment of inertia, generically we can calculate by using this expression. This is general expression of moment of inertia, IR mr squared. When I say general, it means that whenever object does not have a specific geometry, such as in this figure, a thin shell, solid cylinder, hollow cylinder, a rod, rectangular plates, or even sphere and shell, then go for the calculation of the I value being mr squared. However, if it's mimic to any of this geometry, then this table need to be referred to. So you will find that every geometry has the calculation of the inertia, and in this case we call it as moment of inertia, accordingly. So you need to look at where is the axis of rotation. In the case here of the first figure, axis of rotation is exactly at the center. What about this one? Again at the center. However, for the thin long, which is 1/3 here, the axis of rotation is somewhere at the end. Now let us look at example 10.4. The aim of the example 10.4 is to decide which expression of moment of inertia to be chosen. That's number one. And number two is to relate with the expression. Okay, now by looking at this figure, this is where the period, or you can say is here, is the axis of rotation. Now hold your hand, curl your hand, and you will find that your curl finger is in the direction, so this is your fingers. So your fingers would somewhere like this. And you find that your thumb is into the page. So since it's into the page, the directions of the torque for this is actually a negative product. Now, by correlating it with the idea of I alpha, that torque is equivalent to I alpha, we find that our torque is actually a negative value. However, since it's just a singular torque here, that's the reason why this question omitting the negative, because it's not interested. However, if you would like to go through the process together with the direction, feel free to do so. Tak ada masalah pun. Alright, let's now look at again the object itself. What does it mimic? This geometry shows a long rod. And it's pivoted at the end. So this really makes or similar to this one. And hence the calculation of our inertia would be, or moment of inertia would be 1/3 mass times its length squared. And 1/3, look here how they choose. This question chooses the expressions. and then the rest is just calculation. How about the rest? This is I alpha just now. How about this one? This is actually coming from the expression of F times lever arm. Oh, perhaps I should write it the other way around. R times force and times with the sine theta. In our case, recall that the angle must be between R and F. Let's go back to our figure. We find this is our R value, which is half of the length. So half of the length, this is our R, and the angle between them is perpendicular, sine 90. So as you simplify, you find that R become L over 2, while the force is equivalent to just now M times G. Now the expression here, we're going to modify and then combine with something you have learned earlier, which is linear quantity. What are our linear quantity? Number one, S is R theta, V R omega. So this is V tangent. And finally, A tangent is R alpha. Now from this expression, shows that alpha is A tangent over R. Now let's fit this expression into here. However, we must understand that R here is equivalent to L. R is actually an equivalent to L value. And therefore, it looks something like this. A tangent. This is the general expression that the lever arm is L. So as you simplify, you find that we can cancel away or take away L, and simplifying that A tangent is at the same time equivalent to 3 over 2 G as in the expressions. In example 10.6 here, you need three expressions that you have seen earlier and combine them into one another. Number one, the linear expression of A and alpha. Number two, generic idea that thought is I alpha. And finally, something coming from the Newton's second law for an object. So the situation is as in the figure, like this one. And they explain that we have a wheel, and the wheel has moment of inertia I. At the circumference, there is a string attached to it, and hence you're supposed to observe and understand by this object, pulling object here attached to the string, and hence the force applied to the circumference, which in this case producing the torque, is due to the tension here. Jadinya kita nampak tension this tension of the string is the one which apply torque to the wheel here. So here you find that when the wheel is released, the mass at the bottom will accelerate downward. So as this object M falls down, dia akan pull the string and resulting the cord to unwrap of the wheel, and the wheel akan rotate in angular acceleration. Jadi ceritanya it has an angular acceleration because now the tension is applying torque to the whole wheel. So your task is to get an expression where angular acceleration is how much, okay, by relating with the tension and also acceleration. Okay, where are those values? Number one, let's start with the torque. Torque is I alpha. However, at the same time, I alpha is also equivalent to RF or FR. So here, F times force and R. the R we are talking about, this is the generic expression. This is the symbol used in this figure. So R. And then the force that we are talking about is this force. This is the force that apply torque to the system and allow it to rotate. So that's the reason why we are going to write it down as T times R or R times R times T. So as given here. So this is our first expression. The second expression is coming from the second object. Since the object is falling down, so we find that the net acceleration is, or the net force is in the negative direction. And force upward is positive, downward is negative, becoming T minus mg equivalent to ma. Now, the next tips, having this as the second expression, my next tip to arrive with this expression is very simple. You can follow as steps given here, or what you can do is we are going to isolate the T, so becoming this mg minus ma. Now this expression we are going to sub into the first expression. Okay, now as we sub, we are also substituting another expression. So we have 1, 2, and then we have another third expression. Our third expression is this one. This is our third expression. A is R alpha. Now, with that A as R alpha, so this expression, A, R alpha, the R alpha just now is the generic expression. To fit in symbol inside this equation, R is capital and then alpha. So now our second expression will be simplified, becoming mg minus m r alpha. What to do with this expression? Yes. So you can either adjust from the very beginning or straight away later after the substitution into equation 1. So as you substitute, your expression will turns out to be something like this. The I alpha and then the tension earlier, so mg minus m r alpha and then times with r. So this expression later on, I want you to simplify that alpha would be ataupun factorizekan alpha dia. So you have mgr mr squared alpha is alpha, and therefore I alpha is plus alpha mg r. So alpha I mr squared mgr. So you find that alpha is mgr over I plus mr squared. Now, though it looks different, but actually these two equations is equal to one another. They are equal to one another. So not to worry. My concern is for you to see number 1, number 2, and number 3. More than enough. Okay, give it a try. Now I have here very similar example with the same equation but with an additional equation, which is number 1, I is equivalent to what? Here you will find that you are using wheel as well, where this is the wheel and the wheel will have the I, which is equivalent to half mr squared. The moment of inertia belonging to that is half mr squared. How do I know it? Because the wheel resemble this one, a solid cylinder. Dalam dia penuh, solid, penuh, fill up. So 1/2 mr squared. The rest are quite similar. So let's now look at this example. Okay, let's look at the question and identify keywords here. So this is a solid, uniform, frictionless, cylindrical reel where mass is given as 3 kilogram and radius 0.4 meter. So it's used to draw water from a well where bucket is 2 kilogram attached to a cord that is wrapped around the cylinder. Find the tension. So calculating the tension, remember earlier, so it should be negative T. Okay, ours is by using this version. T minus mg equivalent to negative ma. However, we arrive at the same thing. Alright, so simplifying it, you can get the value of the T. However, you will find that to get the T, you do not have the value of acceleration. So this equation is not enough. So hold on to this one. What's next is you need to look at the concept of torque. Torque is I alpha. So I would be given. So this is the value of I. Half mr squared and then alpha. Okay, now what's next is you should see that alpha is equivalent to the one you have seen earlier. A is R alpha. Alpha is A over R. Okay, A tangent over R. So this is the same thing here actually. So with that, okay, let's substitute, partially substitute here, or perhaps leave it here pun boleh. Boleh tengok sikit. Because belum siap lagi. This is our 1, 2, and then we have another which is coming from the torque itself. So beside having I alpha, torque is also correct to have it as T tension times R. Observe as well this diagram that this is the lever arm which is R, and it makes 90 degree with the axis of rotation. The lever arm is 90 degree with the tension. So that's why you don't show it here, because sine 90 is 0. Sine 90 is 1. Now, why is it that it's negative? In terms of the direction, hold your hands, curl your hands, you will find that your thumb is directed, torque awak akan dia buat macam ni kan, curling. So, your thumb is into the page. So, you'll find that this is direction is negative torque. So that's indicated here. So half mr squared alpha. Now just now I did mention bahawa you boleh modify, masukkan A just now. So this is what they did just now. Alpha ni dia gantikan sebagai A over R. So A over R. Jadi kita boleh, R ni is actually the radial arm just now, symbol used tadi. Jadi kita boleh potong and simplify. Sampai kat sini, of here, combine all these. You have 4 sebenarnya all together. Dah jadi 4. Kenapa 4? Ingat balik tadi, kita ada I value which is 1 over 2 mr squared ya. Ni alpha, ni tension, and then kita ada torque just now. So yang number 4 ni adalah, siapa yang get lost torque at the same time is F time R. Okay. Ada sine, of course. When sine is 90 degree, kita tak nampak effect dia lah. So when you simplify, this torque is tension times R or R times T. Nevertheless, it's just the same So substitute, cuma torque tu tadi kita ada arah, dia ada negative value. So this is the negative value just now. And then kita simplify, solve it. You are going to arrive with acceleration and T value. Okay, give it a try of. Yang penting nampak equation ni susun masuk dalam expression. Okay, one single expression. Okay, next one. If the bucket starts from rest at the top of the well and then falls for 3 seconds before hitting the water, how far will it fall? This requires us of the kinematic expression. Cuma bezanya from this kinematic expression, kita nak masukkan nilai A as negative 5.6. Dan T sama juga dengan 3 saat 3 seconds squared. And since it fall from rest, jadi U ni akan nilai dia kosong. So that's arrived with negative 25.2 meter. Maknanya daripada kedudukan asal ke atas, dia jatuh sebanyak 25.2 meter di bawah. Now for 10.6, calculation of moment of inertia, it was only merely about the concept. However, tadi sebenarnya with that example, the additional example, kita telah discover how the technique is done. Cuma saya nak simplify kan. If you have a geometry, specific geometry, you kena refer back to the table. Now, where do you get the table? Dalam exam kita akan bagi. On the other hand, kalau dia adalah very generic, tak ada menyerupai mana-mana geometri, maka use this version mr squared. So this is a very general rumus sahaja, mr squared. So that's exactly, kita wrap up the idea of moment of inertia tu dalam bentuk begitu. Kita guna rumus mr squared untuk general. Kalau dia ada bentuk-bentuk specific geometry, baru kita refer to the table and then go by that expression. Okay, untuk calculation of moment of inertia, kita akan buat lebih banyak lagi dalam subtopic ataupun chapter 12. Okay, that's it guys. Thank you.